that a residue here doesn't interact with a residue over there. In all of the places in the phi-psi map, all of the allowed places on the phi-psi map, the chain is much more contracted. And when it's contracted, it has opportunities for a residue to interact with other residues that are nearby, but not strictly nearest chain neighbors as Florey had thought. And that's what Rohit discovered. And so, having discovered that, it's clear that there's more organization in the main chain than we had previously thought, and the question is, what kind of organization? Nick Fitzke, when he was a graduate student, Nick has gone on to bigger and better things. He's now a postdoc with AdVac, sitting back there in the audience. When Nick was a graduate student in the lab, he decided to find out what kinds of interactions these might be. And he found a number of them. Here's a particularly dramatic one. An alpha helix can't be followed by a contiguous beta strand. What does that mean? It means that if you had 3 consecutive residues in this part of the phi-psi map, so there's alpha I minus 3, I minus 2, and I minus 1. And you take the next residue and put it here in that part of the map, you get a steric clash. So it's not a nearest neighbor steric clash, it's an I to I minus 3 steric clash. But nevertheless, it's a steric clash. Furthermore, it's a steric clash between the backbone carbonyl oxygen of this I residue and the backbone carbonyl oxygen of the I minus 3 residue. So it's a backbone-backbone clash, which means that regardless of what residues you have there, since it's backbone-backbone, you will get that clash. Now, this is an odd kind of result because it's very simple. So if you show this to a theoretician, the theoretician says, well, I know I could just relax the phi-psi angles ever so, and I could get rid of that clash. But you can't. And the demonstration that you can't is what Fitzke did. That's why this is a paper, not just a picture. So you can't get rid of the clash. And if you talk to an X-ray crystallographer who spent a lot of time looking at proteins on the screens, they say, well, I think I knew that because I never see in a salt structure that a beta strand follows immediately after an alpha helix. There's always an intervening turn or loop separating them. And this is why. Why does this matter? Because these are the 2 most populated regions in the phi-psi map. And they're by far the 2 most populated regions in proteins. So it shows you that a huge number of conceivable conformers that you might have, that you could have either an alpha or beta, either an alpha or beta, either that. If you had that, many of those have to be eliminated because if you had 3 consecutive residues anywhere in this region of phi-psi space, the next one can't be there. So it imposes a kind of organization not just on folded proteins, but on unfolded proteins as well. And so it also shows in a very palpable way that there can be systematic local restrictions that extend beyond adjacent chain neighbors. Here's an I-4. Well, Dr. Fitzke went on to ask himself whether this is a singularity, and it turns out it's not a singularity. He identified many other kinds of conformations in which you either get a steric clash, or alternatively, you get a conformation in which you couldn't solvate a backbone polar group, either by making an intramolecular hydrogen bond or a hydrogen bond with water. And that would be a high-energy structure and would be eliminated, largely eliminated from the population, as we will come to in a moment. Well, if that's true, then what about all of this wonderful work that Florey and Charles Canford did, showing that the unfolded, one can write an equation, a simple equation, here is that equation, for what the mean square radius of gyration would look like for a population in good solvent, if it's a random flora. And Canford's subsequent work showing that, in fact, the folded structure satisfies this equation. So this equation says that the mean radius of gyration that you will see for this population goes as the number of residues in the polymer times some prefactor raised to an exponent, and a good solvent, that exponent should be 0.6. And in fact, that's what Hanford and subsequently other people like Sebdoniak and Kevin Plasko have found when they've done small angle X-ray scattering, where you can back this exponent directly out of the experiment. Nick Fitzke then said, well, I'll make up a contrived example. Exactly fixed in rigid X-ray structure, 8% is allowed to wiggle. You now generate random chains by wiggling a protein of known structure at these wiggle points. When you do that, if you get a steric clash, you throw it away, and you keep doing it again and again until you get a representative population of random chains, but only randomized at this 8%. Only randomized at this 8% of the chain. Now, you can do a mean square radius of gyration on that population. And you can do it for not just one protein, but you can do it for any number of proteins whose X-ray structures you know. And when you do, strangely enough, what you find, not so strangely really, what you find is that you get an exponent of 0.6. So these are certainly not proteins lacking organization. They are random coils in the strict sense of random coil. After all, when you think about it, anything is a random coil if you make it long enough. If I take a steel I-beam and stretch it from here to the moon, it's going to behave like a random coil. The question we're arguing about is at what chain length does it begin doing that? So what Fitzke found is that proteins that are held largely in their native conformation are nevertheless satisfy this Flory equation. So what you realize is a kind of broken syllogism. A hypothetical random coil that lacks any organization has a radius of gyration with an exponent of 0.6. Unfolded proteins also have a radius of gyration with an exponent of 0.6. And therefore, says the syllogism, unfolded proteins lack organization. But that's a broken syllogism. It's like saying, my first name is George and I grew up in Texas. George Bush's first name is George. He grew up in Texas, and therefore I'm George Bush. And it's broken. I'm grateful for that. Okay. Next big question. Folding arises predominantly in the native side of this NTU equation. The side chains really have to do all the discrimination because the backbones are essentially all the same. So now we're going to take an excursion into adaptive biology. So the adaptive biology community has for years been studying organic osmolarity. And Wayne Bolin, Tom Record, several others have taken up the physical chemistry of these small molecules. So I want to talk about organic osmolarity for a moment. So what are organic osmolarity? They're small organic compounds. They have no net charge. They come in all kinds of delicious flavors. Here's trimethylamine oxide. Here is an amino acid. Here's a sugar. Here's another sugar. There are alcohols. Here's urea, the common denaturant. It's an organic osmolarity as well. These are found in all species in nature. They're found in all three kingdoms in nature. And they were there from the very beginning. And what do? What they do, the adaptive biology community is interested in them because they provide some kind of organic ballast to keep the cell from rupturing osmotically.